Welcome! In this video we will be talking about roundoff errors, truncation errors and true errors. And by the end of this video you will be able to identify roundoff errors and know their consequences, and you will be able to choose appropriate number types. So let's start talking about errors. Usually our numerical solutions are not exact. Why is that? Well, there's predominantly two sources of errors in our numerical methods. The first one is due to the fact that we only have a finite number of bits available to store our numbers, and that type of error is classified as a roundoff error. And then there's a second type of error, the so-called truncation error, that we will talk about in a subsequent video. So here we're going to focus on roundoff errors. What's the cause for a roundoff error? Well, like we saw in a prior video, we only have a finite number of bits available to store the mantissa. Numbers that would require more digits therefore cannot be stored exactly. And this roundoff error is actually of the order of the smallest difference that a computer can tell between different numbers. And in this prior video where we talked about number types, that smallest difference between numbers we identified as 2 to the power p, where p is the exponent of the number that we're looking at in engineering notation, minus m, and m is the number of mantissa bits that we have available in our number type. So how can we shorten our numbers if our mantissa would require more bits? How can we make longer mantissas fit into our number types? Well, there are two options. The first one is chopping. Well, that means simply discard any extra digits that you would have to store. So here's an example, and we're going to stay in decimal numbers here to make it a little bit easier. So the number 20 over 3 would require infinitely many decimal digits to store. 6.666, and the number 6, the digit 6, would repeat infinitely many times. Let's say in decimal we only have 3 digits available. So we would take the first 3 digits, 6.66, as an approximation to 20 over 3. And if we're chopping, then we're just discarding all the following digits. Rounding, on the other hand, works a little bit differently, and you probably all know how rounding works. You look at the next digit, and if that digit is larger than 5, you will round up. You will increase the last digit you have available to store. And if it is smaller than 5, you would just basically chop the numbers away. So in our example, we're going to look at 6.666. That last digit that's marked there is 6 is larger than 5. So therefore, the third digit would be rounded up. And we would approximate 20 over 3 as 6.67. Now in both cases, we have made an error, right? And that is called the roundoff error. Let's define the error as the true value minus the numerical value. So if we do chopping, then the error would be the true value, 20 over 3, minus our numerical value, 6.66, and that error would then be 6.6 and 666 and so on times 10 to the power negative 3. For rounding, the error is the true value, 20/3, minus the numerical value, 6.67. In this case, the error that we make when we round is 3.333 times 10 to the negative 3. Now, this error doesn't really seem like much. But remember, if we perform a large number of operations, roundoff errors that we make in each one of these operations can accumulate and become very large over millions and millions of operations. So here's another example where roundoff error matters. Let's say we have two different numbers, the number a, which is shown here, 1.025432, and the number b, 1.024567. And we want to calculate the value of x, which is 1 divided by a minus b. Now, if we use MATLAB or you use a calculator that uses double precision numbers, you can type in these values and you would get that x is 1.15606 and so on. You can see the digits here times 10 to the power 3. Okay, let's do chopping with these numbers and see what the results is if we chop to 5 digits. So if we only have 5 decimal digits available for the numbers, then of course we can't store the entire number A or B. We would have to chop that number. And that chopping would be to 5 digits. So the number A would be 1.0254 and the number B would just be 1.0245. Now let's plug these numbers in, do the calculation, and chop the result. And the result would be 1.1111 times 10 to the power 3, so 1111.1. Okay, now if you compare that to the result that MATLAB gave us, and let's just assume that MATLAB would be the true answer, which unfortunately is not, but let's use it as a standard for the true answer. We can calculate the error of our chopping to 5 digits, which is 44.9582. Now let's do rounding to 5 digits, right? In order to round, we have to look at the 6th digit and decide whether the 5th digit has to be rounded up or not. So in this case here, the number A, the 6th digit is a 3, so we keep the 5th digit as a 4. But for the number B, the 6th digit is a 6, so we will have to round up this number from 5 to 6, that last digit. So the number B rounded to 5 digits, it's 1.0246. Now let's type these numbers into a calculator or MATLAB, and we find that that value now, that x would be 1.25 times 10 to the power 3, so 1,250. And if we use our MATLAB value and we calculate the error, then in this case for rounding, the error is actually 93.93 and so on. So it is larger than the error that we had when we were chopping the numbers. So it's not quite obvious that for all types of mathematical calculations, rounding is always better than chopping like we saw in the first example, because in this example here it turns out that chopping would actually be more accurate. Now, why is the error so large here? Remember, we had 5 total digits, and our error is of order 10. It's 44 or 93. Why is this error so large, even though we have 5 digits available? Well, there's 2 reasons for it. The first one is that we are taking the differences of numbers that are very similar. And if we take differences of numbers that are very similar, then the roundoff error becomes actually important. Because remember, the magnitude of the roundoff error depends on the magnitude of the number. So we have 2 to the power p minus m. And the worst case scenario is that we take the difference of large numbers. Large numbers means that the exponent in the engineering notation p is very large. And in that case, that difference, that roundoff error becomes very large because 2 to the power p minus m, the p becomes large. And then there's a second issue here in this example, in that we take the difference of numbers that are very similar. The result will be a small number that is prone to roundoff errors because the numbers are similar. And then we divide by this small number. Because we divide by a small number, the result will be a large number. That is the predominant reason why our error here is actually quite large. So what's the consequence for this? The consequence is that do not ever compare floating point numbers that are the results of computations using the equal sign. Because due to roundoff errors, the number that your numerical method could give you might actually be different from the analytically exact number that you can calculate. And instead of using the equal operator in MATLAB to compare 2 floating point numbers, if you want to know if the 2 numbers are equal, right, close to each other, what you should check is the difference between the 2 numbers, the absolute value, whether that is smaller than some small number epsilon, of the order of a factor times the smallest difference that a computer can tell apart. Now let's do one last example here highlighting roundoff errors. So we have this quadratic equation here, x squared minus 100.0 0.00001 times x plus 0.01 is equal to 0. So that's a quadratic equation. And you probably recall the quadratic formula to find the analytical solution to a quadratic equation. It's just given here, right? There are two solutions, one with a plus and one with a minus sign in front of the square root. If I plug in the values for a, b, and c from the quadratic equation, so a being 1, b being negative 100.0001, and c being 0.01, I will get the exact answer that x1 would be 100 and x2 would be 1 times 10 to the negative 4. Now let's plug these formulas into MATLAB. And what you'll see is that x1 is 100. Well, that's the analytical solution as well. But what you get for x2 is not 10 to the negative 4. It is pretty much 10 to the negative 4, but then there's a whole lot of zeros here, but then there's 33197 over here in these last digits, which really shouldn't be there in the analytical solution. So we have made an error here, right? Why did we make this error? Well, in the prior slide, we talked about what could be causes for round-off errors, and one of those causes was we take the difference of large numbers, and that's exactly what happens here. So where do we have a difference here? Well, it's actually here in this numerator terms. We have negative b, b being a negative number, so we have negative, and negative is 100.0001 minus the square root. And if you plug in the values for the square root, you get minus 99.999899. So you take the difference of large numbers, where 10 to the power 2 order 2 numbers are kind of large, even though they're not humongously large. We take the difference of these numbers, right? And that is prone to round-off errors. So the culprit for this round-off that we see in the solution is taking the difference. Can we somehow get rid of this difference in the formula? And it turns out that sometimes, or even often, we can. So here's the example, right? The culprit is this formula over here that we have this difference here in the numerator when b is negative. So let's do a trick. Let's multiply this equation by 1. Okay, the 1 is written a little bit more complicated here, so I have the same term here in the numerator and the same term in the denominator. So I'm just multiplying, in essence, this formula by 1. But if I do this, right, you see maybe here this binomial formula, minus b minus the square root times minus b plus the square root, right? So if you multiply these together, you get the first term squared, so b squared minus the square root term squared, so minus b squared plus then the 4ac. And in the denominator, we just have 2a times minus b plus the square root term. Okay, so if you look at the numerator here now, we have b squared minus b squared, that cancels out. And the 4a in the numerator now cancels against the 2a, just leaves the 2 there. So the final formula, after I did this little trick, is 2c divided by minus b plus the square root term. Okay, so if you look at here the denominator, it kind of looks like in the denominator now I have a difference. But that's actually not true, because b in our example here was negative. So minus a negative number here is a positive number, plus the square root is always positive. So we don't have a difference anywhere anymore in this term. And if you now use this formula and code it up instead of the original formula up here that we used to start and calculate the first result, you'll get that MATLAB tells you that x2, the second solution, is actually now 10 to the negative 4. So it has not this round-off error in it anymore. Okay, so with that in mind, that we have these round-off errors in our numbers, which of the number types that we previously talked about should you use? Here is again this table that defines these different number types from IEEE 754, half precision, single precision, double precision, and quadruple precision, and then also the B-float 16 number type. So which number type should you use for your application? Well, you should use enough bits to satisfy the precision requirement of your application, right? So that roundoff errors don't pollute your solution. And you should choose a number type that has a number range from the smallest to the largest possible value in your definition that is compatible with your application, okay? Now, that would push you to use as large a possible number type, right? As many bits as possible, right? Because you would be more accurate and you would have a larger number space available. Counteracting this is cost. So what you should really try to do is you should try to use a number type that is supported by the hardware that you're using to solve your problems. Now, CPUs nowadays typically are all double precision. GPUs, if you do computations on GPUs, are typically single precision, although there are some accelerators that are double precision in hardware as well. There are some artificial intelligence machine learning hardware chips, some custom processors basically that are built for half precision or B-float 16 arithmetics. And that kind of forces you or pushes you towards one number type. Now, there's one other thing you should bear in mind, that you can typically always run at lower precision on the hardware that supports higher precision at the same speed. So if you have a CPU that can do double precision, you typically don't lose any speed if you use single precision or half precision. However, if you want to run higher precision than is supported by your hardware, then that typically can only be done in software, and that comes at a quite substantial speed penalty. So while our standard CPUs do support in hardware double precision, if we wanted to do quadruple precision, that can be done in some programming languages like Fortran, but that comes at a cost that all of these operations now have to be mapped into double precision numbers at additional cost. So here are some examples. If you do general scientific or engineering computations, those nowadays are done in double precision. If you still have some legacy code, some legacy Fortran code, for example, oftentimes these are done in single precision, but probably in the last 20 or so years, the shift has happened to double precision. MATLAB by default actually uses double precision arithmetics. If you're interested in machine learning or AI applications, those are typically done in half precision or B-float 16 numbers. And oftentimes there is custom silicon that supports this at very fast speeds. If you want to do extreme scientific or mathematical computations that really need additional accuracy, then you would opt to do quadruple precision. And we will actually see at least one example in this class where we will hit the precision limit of double precision numbers, where you would then go to quadruple precision. All right, that's it. Thank you for watching.